All right. So we have Danny McPherson here with Arbor Networks. He's going to be presenting the first one here on BGP Scalability Considerations. So, also, before we start, one last thing. The break, give a thanks to Savis for taking care of the break there. And also, if there's any, Aaron has a help desk out in the hallway, so if there's any questions or anything of that matter, they're out there. You could go see them. I think it's out there on this floor or the floor below. And here's that, Danny.
All right, so can you hear me okay back there? Good. So I'm Danny McPherson. I'm with Arbor Network. Shane Amante isn't here, unfortunately. It's the bad news. The good news is I'm a much better kisser than Shane is. So, all right, nobody's paying attention already. Forget it. All right. Anyway, I'm going to talk about some BGP scalability stuff, and hopefully, you know, if you're an operator or an implementer or a protocol designer, you'll find some value in this. I'm going to focus a lot on intra-domain routing scalability as opposed to inter-domain, and I'll talk about why in just a moment, and then some other info. One thing to note is that the slides available online that should be posted now in PDF form have about another 15 slides or so in here that provides more tutorial nature sort of content, and so if you're following those, then they're going to be slightly off from this. So one of the things that that I did in my operator days was try and help with some of the scalability stuff internal to some of the networks I worked on, and a lot of that was minimizing the number of unique routes in the network as opposed to the DFZ size or the number of the number of fib entries and so forth. And I'll talk about all this in a moment, but. One of the challenges that you see on the academic side in particular is that most of the academic approaches that you've seen to date on studying BGP deal with a single external BGP analysis or external BGP analysis from lots of different points in the internet, like some of the the University of Oregon route views and those sorts of things. And those are fine. The problem is that though inside the core of IBGP networks, scalability is a much larger concern. And much different issues. The dynamics internal to a BGP mesh are very different than a single external view where you're only sending the best path and so forth. So I want to talk about some of why this matters in a moment. So what breaks first? The thing you hear everybody scream about is DFZ size and fib size, and absolutely that's a huge issue. Ultimate fib size is considerable. How big is the fib? What's the impact of V4 and V6 and so forth? But there's a second issue there, which is which ultimately equates to the rate of the churn of that fib size, which is the number of unique routes in the routing system. So you have a prefix and you have a route, and or you have multiple routes to reach that prefix. So you could have multiple paths for a given prefix via different ASs or with different cluster lists or different attributes inside of a BGP topology. So the more routes you have, or the more unique paths for a given prefix, the more state and the more churn and the more I/O in the fib and so forth that you're going to have. So if you look at this actually came from Level 3's network, and over the past 10 years or so, and it's basically charting the fib growth, or DFZ size, more or less. In other words, the unique routes in the routing system and the number of paths in some of the routers in their network. And there's some more detail available on this that I'll provide a point or two later. But as you can see, the point here is that the number of unique routes is growing more steeply than the DFZ size, and the number of unique routes has explicit implications on the scalability of everything from the CPUs and the churn in the routing system to the security of the routing system to the fib sizes and fib I/O and line cards and all this stuff. I'll show you in a diagram in a moment. So this busy diagram here, what you're basically looking at, this is sort of my stab at a conceptual router architecture. And in the top left column, what you see is your BGP routing table, right? And you got an JSON rib in for each peer and a decision process that picks your best BGP route, and then a JSON rib out for each peer. You got like an ISIS link state database or OSPF, a static one, and so forth. Then you have some kind of routing table manager that sort of orbits between those and says, I'm going to prefer static routes over BGP learn routes and so forth. And then finally, you've got your IP rib, which is all the stuff compiled and all the best routes from each of those different processes. And then the fib, which is what you're going to use to forward information. And then in most modern routers, like Type 2, Type 3 switches, you have a distributed fib. So you take that, that forwarding information base and you push it out to a bunch of different line cards where forwarding decisions are made independently of a central processor. So today what you basically see is in the core of most of the decent sized BGP networks, anywhere from 2 to 6 million paths, right? 2 to 6 million unique routes in those, in the BGP routing table. So if you do a show IP BGP summary, it'll say X number of network entries in iOS and something, show BGP summary in JunoS, whatever. And you'll see, you'll see X number of network entries. So that's talking about all the unique routes in the system. And then after those are sort of, analyzed, and you pick all your best BGP routes, those are given off, and then they become the IP rib, and then that's abstracted down, and some link layer forwarding stuff's put on, and it's put in the fib, and the fib's what's pushed out to the line cards with a little extra information. So one of the things is that, you see this red arrow here, there's a slight bit of animation, but basically any change in a best path of those 2 to 6 million on average results in a change all the way down in the system. And every one of those red arrows you see there from that loc rib on down are usually sort of multi-transaction stuff. In other words, if the rib changes and you put something on a fib, it's not just pushing it out. There's multiple transactions like, some kind of commit and so forth. So it's pretty heavy processing there for each one of these, right? So the more routes you have in the system is going to result in more churn all the way down to the fib. So why is the number of, unique routes increasing faster than prefixes? Basically, one of the primary reasons is denseness of interconnection. The more available paths you have, the more interconnected the internet is, and the routing domains make up the internet, the more available paths you're going to have, and so you're going to have more more routes, more unique routes in the routing system. So this is going to illustrate that for you. So you got this top left cloud here, which is an enterprise, and they have a prefix, P/24, and they connect to an ISP, ISP1 in this case. And they advertise their one route to ISP1. Well, ISP1 interconnects with ISP2 and ISP3, and they actually interconnect in multiple places, say 10 places, right? Well, this isn't one prefix or one unique route in that routing system. What this ends up being is 22 routes in ISP1's network. That's just at the edge, the egress perimeter of the network, the eBGP perimeter of the network. That's not inside the routing system, inside of ISP1's AS topology, which is actually what I'm going to talk about. So, everybody talks about route reflection. Says, well, route reflection, doesn't that give you some implicit aggregation over a full mesh? The point of route reflection and AS confederations, for that matter, were to help with scalability of BGP. In other words, BGP has this rule that says that inside of a routing domain or inside of an AS, a BGP speaker has to be fully meshed with every other BGP speaker. Or actually the rule is that if I'm an iBGP speaker and I learn something from another iBGP speaker, I can't tell a third iBGP speaker. So that means they have to be fully meshed, or you have to have some hack like route reflection or AS confederations to get around that rule. So, so basically, route reflection is one of the ways to get around this. What else do I want to say? Let me just illustrate it. So a common topology that you see in networks is a single layer of hierarchy with route reflection. So you have the blue routers down on the left side there, and then each of those blue routers is referred to as a route reflector client in this case, and they peer with route reflector servers, or route reflectors, the gray routers in this case, and then you'll fully mesh the gray routers or the core routers. You may add another layer of hierarchy. I've seen as much as 4 or 5 layers of route reflection hierarchy in some networks. There are advantages to that, and there are also disadvantages to that I'll talk about in just a bit. But it's sort of a typical topology there, and it gets away from the fact that every blue router would have to be interconnected with BGP with every other blue router, and you have to maintain TCP state and so forth. So busy slide here, but basically, there's been a lot of work done to look at instability in the routing system. And a lot of this instability is, from that single BGP perspective. You don't understand what's happening inside of a network. All you know is that you get these, these extraneous updates external to that routing system. And so let me illustrate this. Basically, you got a prefix down here again, this P/24, and it's that enterprise that connects to a route reflector client. And he advertises a route, and he gives it to these 3 route reflectors in the network. Well, each of those 3 route reflectors actually give it to every other route reflector. So that implicit aggregation thing you thought you had, what you got now is you got 3 copies on the route reflectors, and then every other route reflector in the network now has 3 copies of that one prefix from that one advertisement or ingress point in the network. So you get, a 3x amplification factor. But what happens here is these route reflectors in the top in this case, in that cluster 3, advertise the route. They pick one best route. This is the implicit aggregation thing you get through route reflection. So they pick one best route to pass on to their clients, and in this case, it's that top blue router. Well, what happens is if the route reflector goes away for some reason, say that router crashes, even if it's not in the forwarding path, then you got to pull those announcements away and you got to advertise a new one, right? Well, the problem here is that anytime even a non-transitive attribute, something that you don't advertise outside of your AS, is changed and results in a new best path BGP selection, you still send that to your external peers, right? So when this question mark up here keeps getting these copies of this duplicate update, and when there's lots of instability in the network, then you see, he may get 5 or even 10 copies of that update just because one router failed or one link failed in the network. And if you use things like BGP route flap dampening, which some people do, some people don't, with varying thresholds and penalties and so forth, then that one update or one change at some point in the network could result in 15 or 20 or 50 updates at some egress point in the network. And each one of those updates, because they're per prefix, they're not path and attributes and so forth. And even if they were, they wouldn't be non-transitive attributes that are never leaving that blue router and going to another network. Then, then it would be penalized and it may be suppressed because one change in the network. And so, so that's an issue with this. We did a study, actually. There's a paper that we submitted to IMC with Lisa Zhang and Jonathan Park and some of the UCLA folks and on level 3. And we took some of this University of Oregon route view stuff, and we took an IBGP feed from inside the network. And we looked at the instability and said, how many of these changes are we seeing at the University of Oregon that we're, how many changes are we seeing inside the network that we're not seeing at the University of Oregon route views? And how many attributes are there? So basically, during the busiest time of BGP instability, 97% of the updates that are received are exact duplicates, and each one of those exact duplicates are going to be penalized if somebody's employing route flap dampening, for example. So there's a lot of instability there that has no point. There are some implementation optimizations and some network architecture changes I'll talk about in a bit that you can change to make this a little more stable, in particular during times of instability. So here's basically a graph of this illustrating what I just said with the CDF on the right side there. And it's basically just saying that during the busiest 0.01% of the time, 97%, 98% of the updates are exact duplicates. And, and so that's not a very effective protocol. And, in particular when there are times of instability is when you want to try and be the most effective in what you do. So. And for those wondering, these were not caused by session resets. We had ways to qualify and quantify that when we did these measurements, and that's illustrated in the paper itself. So one of the things that's frustrated me, a considerable amount is when you make implementation changes, like, for example, a router operating system change that focuses on optimizing the system locally to save some CPU resource, but it doesn't think about the systemic effects of that. So an example of that is a change in BGP route reflection from RFC 1966 to 2796. And when route reflection was initially defined to get away from the BGP scaling, the full mesh BGP scaling rule, basically the thing that was, it had to be backwards compatible. So what happened is those clients we had in that earlier picture didn't have to know that they were clients. The route reflectors had to know they were route reflectors, and if they told someone else they added a path vector to this to illustrate that it was a route reflector, but the client didn't have to know it was a client. Well, in RFC 1966, that's how it handled this because it was looking for backwards compatibility. RFC 2796 was actually updated and removed this rule so that a route reflector could reflect a route back to a client that the client just told the route reflector. And it doesn't seem like on the surface that was a big issue, but I'm going to illustrate why that can be a big problem in just a moment. And let me just show you now. Here. So you've got your clients in the blue down here, and then the gray are your route reflectors, right? So normally the way this worked is the client, the blue client here, would tell the gray routers, he'd say, hey, I got prefix P/24, and he would tell his route reflectors. Well, his route reflectors, each one would tell everybody else, right? They couldn't tell the client again because that would be a routing information loop. In other words, he's receiving something back, and that router may install it that he advertised. And so the route reflectors had to know not to send it back to the client, and it did this with some new attributes that were added to route reflection. Originator ID was compared to the router ID of the client and so forth. I don't want to get into that right now, but I can certainly talk about it if you like. But one of the things that the change to the spec made was that these route reflectors can now tell the client. On the surface, it's like, that's fine. It's not a big deal. The client can drop these updates, and it's not going to hurt anything, right? Well, it actually can hurt something. So if you dig into that client and look at what's happening here, right, what happens is this router, which is an external peer on the far left side, the little router, advertises something to the big router, and he tells the 3 route reflectors, right? What happens is they all start telling telling the client back, right? And each peer, each update is serviced in a round robin fashion, right? So you get these updates in, and say you have 100,000 eBGP learn routes. So the client starts processing those, and he goes 1, 2, 3, he gets to about 10, and he starts advertising them out to his route reflectors. Well, the route reflectors start sending all those back. So if you got 100,000 and he's on 99,990, and he starts receiving them back from the route reflectors, he has to process those just like anything else. So those will be in the same queue and the same processing as the legitimate updates that are coming in from the eBGP peer. And so you can imagine that in times of instability, or if you want to converge fast, this is very ineffective. Those route reflectors should not be sending those routes back to the clients. Excuse me. One of the other things is that some of the new, like for example, some of the IPVPN capabilities want to minimize configuration. They want to minimize manual or static configuration in the network. And so, like RFC 2547, the IP MPLS VPN stuff was a way to minimize some of that and provide IPVPN overlays on IP infrastructure. One of the things they've done is they want to minimize. So you might have multiple VPN instances or VRFs on a single router, like a single client inside the network, and not want to have to configure static policy between those. So the specification, the accept own community was actually provided that says, well, I'm going to send something in a route reflector, and I want him to send it back. And if this accept own community is on, I'm going to use it to bridge stuff between 2 routers. So it's basically a way to minimize local configuration on a router by creating more systemic state. And that's not effective if you have a large scale network. If those route reflectors were only sending back routes that had the community, that'd be fine. But this actually this actually entices people to make their to write code and be lazy with their implementations and optimizations and reflect everything back and expect the client to drop it, and that's not effective, or that's not a scalable way to to do this. Let's see, network architecture stuff. So cluster IDs. One of the things that Route Reflection introduced was the notion of cluster IDs. And inside of a cluster, you would have your sets of clients, and then you have your route reflectors. And the route reflectors, when it was defined, were supposed to all have the same cluster ID. And what that meant was that if one route reflector in a cluster told another route reflector, that route reflector would drop the update, and he didn't have to store the update because of the cluster ID was a new path vector inside the routing domain. So actually, let me just illustrate this. It's much easier. So basically, here's that diagram we had earlier, right? Where you got your client, you got prefix P/24. He advertises it to the client router, the blue router in the bottom left corner. He tells the 3 route reflectors, they tell everyone else, right? Well, they also tell each other, right? And they're never, ever going to use those updates, right? So if this is 100,000 prefixes from that client, they're all telling each other, each one's going to store 100,000 prefixes, 100,000 unique routes that they use locally, but they're also going to store 100,000 from everybody else that they're fully meshed with inside that cluster. So that's 200,000 in this simple diagram. There'd be 200,000 extra prefixes that guy, or extra unique routes, I'm sorry, that the route reflectors are storing, and they're never, ever going to use those. So if you have unique cluster IDs on each route reflector, that's going to happen. If you have a common cluster ID, those routes are still going to be advertised between your route reflectors, but they're still going to be advertised, but they're going to be discarded when they're received. The reality is that if the protocol was more optimal, it wouldn't advertise them at all. It would say, well, I have the same cluster ID as that guy, and I shouldn't send him these updates because he's going to drop it and we're both route reflectors. So another optimization that could be made there to save some processing overhead. There's lots of other stuff like placement of peers versus customers, number of route reflectors in a cluster. Most people have 2 to 5 route reflectors per cluster. And you got to think, right, for every external prefix you have in that cluster, more than likely there's going to be one best route for each one of those, multiplied by the number of route reflectors you have, advertised to every other router at that tier in the BGP hierarchy. And so there's some amplification, like 5x amplification, or whatever the number of route reflectors you have is. So you got to think about that when you're doing your design. You could add additional route reflection hierarchy. One of the problems, though, is that there are 2 problems actually with this. One is that the length of the cluster list and the AS confederation information for that matter in BGP has found its way into the decision algorithm. And so if you have a longer cluster list associated with a route, even if the data path is more optimal, then the longer cluster list is going to be less preferable than the shorter cluster list. And so that's not that's not something that that's something you have to consider when you're designing hierarchy into your routing architecture. Common and unique cluster IDs. I would definitely recommend common cluster IDs across all the clusters in a given route reflector cluster. Client-to-client reflection versus full mesh. There are reasons you may want one or others of one or either of those. IP forwarding path congruency. One of the other things people are doing a lot today is having overlay route reflection hierarchy. So they'll have some route reflectors at central points in their network and do some policy other stuff on those. That's fine, but if you're using that for sort of generic IP forwarding, you got to be really careful because you can create forwarding loops if you have route reflectors that peer through clients, and so that's something you have to use some caution about. So it's not easy. Another thing I'm going to show you a diagram of or a chart of in a moment is attributes. So one of the things you see all the time is, hey, let's propose a new global community for this. Or let's have unique communities that are transitive and everybody passes them around. And the problem with that is that each one of those means there's going to be a new route in the routing system, right? And if you have unique attribute sets, then you can't do things like BGP update packing where you put lots of prefixes in one update and send one package instead of a unique update for each prefix. And so there are more scalability concerns with that. Other things like, for example, if you peer with someone and they're sending you meds, or you peer with a couple of different AS and they're sending you meds and you're not comparing those meds, or you probably shouldn't be comparing meds between different ASs, you probably want to reset all those because those result in unique attributes and you can't update pack and its unique routes in your routing system. Let's see. Okay, so new address families, I'll illustrate the attribute thing in a moment. I'm kind of on the fence about this one, as many of you are, I think. Lots of stuff from IP VPNs in particular being, sort of the most obvious one to FlowSpec and pseudo wires and L2 VPNs and so forth. But carrying new address family information, using BGP as sort of a signaling protocol, as opposed to defining a new protocol for that. And some people say you're overloading BGP. The alternative is defining another protocol that looks like BGP and has the same state machine and employs a lot of the same functions. And so, so you got to balance this though, right? Because, for example, if you make a change to IPVPN code to reflect routes back to a client for 2547 VPNs, that's the same base BGP code that's going to be used for your global internet routing, right? And so if somebody has some new BGP capability like AS4 pass stuff and it results in session resets somewhere else, that could cause instability in your IPVPN routing infrastructure. So all these things sort of tie in and have dependencies on one another. Effects on attribute growth. So I said something about this a moment ago, but I was pretty big on minimizing the number of unique attribute sets in the network, and you can look at those in your network. But things like meds, it was a common policy to not accept communities from any peers because I'm never going to employ those communities, and to reset meds to the same value. In particular, because early on, some implementations considered a med of 0 versus a missing med as different. One was more preferable than the other. And you shouldn't compare meds between different ASs anyway, so that's a bad idea. But to illustrate attribute growth, you see the top line again. This is a 10-year graph from Level 3's network, and the red line represents. It's obviously not normalized. That's why you see some of these spikes. But the number of unique attributes in the routing system is going to be multiplied by the number of prefixes and the number of unique routes associated with those, and then for each one of these it makes update packing and packaging the more prefixes in a single update more and more or less and less effective. So. Routing security. So here's one that that touches pretty close to a lot of work. That I know that I think Randy was talking about something here, and I believe he is in the security BOF as well, but some other folks. And one of the other things that's especially important to remember is that if you're going to secure the routing system, you have to validate each path, right? You can't just do the prefix. You have to say prefix and who originated it and the path that it came through. And if you introduce more paths in the network or in the global routing system, the denseness of interconnection externally increases, then you have to fully enumerate this when you're defining a routing security policy or a protocol that's going to accommodate that. And so if you design a secure routing protocol today that's going to deal with things like route leaks and route hijacks, then it's not just going to deal with 350,000 updates and origin validation. It's going to have to deal with the paths too. So it's going to be more like an order of magnitude, like 3 or 5 million paths that you're going to have to validate. And and so there's huge overhead associated with this. The other thing is, for those of you familiar with like BCP 38 anti-spoofing measures, there are some ways to automate configuration of that, like with unicast reverse path forwarding. And the only way that'll work is if you accommodate all the feasible paths. And a feasible path is anywhere you learn to route from, right? That's the 3 to 5 or 6 million, whatever the number is. That's not the 350K number that's in the fib. And so if you're going to secure the data plane, either subsequent to or in parallel to the routing system, then then you have to deal with that as well. IDR work. So here's another hot button. Is most of the work in IDR today is dealing with new analytical capabilities or new attributes to solve some new problem, or advertising multiple paths, right? So in other words, each one of those clients, don't just give me your single best path, give me your best path from every external peer. So multiplying it by however many best paths you have from each external peer. So that's going to increase, potentially exponentially the number of the number of paths that you have in the core of your network, right? And so this is going to be a big problem as well on scalability front. There's not a lot of work going on. As a matter of fact, there's no active work in IDR in particular on minimizing the number of paths or the amount of instability in the network. Conclusions, the number of routes in your routing system as opposed to just the number of unique prefixes and the DFZ size and the fib size is very important, and you should be looking at that. There are things that implementers can do. There are things that protocol designers can do, like on the IETF side, for example. And there are things network operators can do to minimize or optimize some of these things in your network. And the BGP stuff, the bottom bullet there is, it's going to bite eventually, and where it's going to make things like BGP security more, or less feasible. And so, it's something that we've definitely got to deal with and be cognizant of now, because it's going to be that much harder down the road if we're not. So. Just some quick acknowledgments. The folks at UCLA published a paper with us, with Shane and I, on a study we did over about a year period on instability and how those non-transitive updates results in lots of external duplicates and that kind of thing. And we talked to a couple of operators on this, and and certainly Craig and Abba's early work on the BGP instability stuff was, it led to lots and lots of people starting to look at some of this stuff. And then a number of people who agreed or disagreed with some of the conclusions in this. And then, level 3 in Arbor for day jobs. And that's pretty much it. I know I went through these pretty quick, but most of the stuff, if you grab the slides, is pretty self-explanatory. And you're certainly welcome to email me, or if you want to participate either in the Global Routing Operations Working Group in the ITF, or IDR, which is where BGP is defined, or CIDR, which is the Secure Interdomain Routing Working Group in the IETF. Any of that stuff, I'm more than happy to provide you pointers. And if you got ideas about other stuff related to this, I'd appreciate those as well. So.
Thank you, Danny. Yeah, we've got probably a few minutes. So,
yeah, probably went a little faster than I needed to.
Hi, Jake Kuhn, Green Hill Software. Could you care to comment on the use of ECMP routes in IBGP load balancing, how that contributes to routing stability?
So today, BGP only sends the best path, and if you're using equal cost multipath on the IBGP side, it's because you have multiple paths you're already receiving, but only one path per peer. And some of the extensions are made to optimize that, where you could even send multiple paths, and so forth. So the only comment I would have there is that if you add more paths to expand things like that, either on the eBGP side, which some people are looking at, and there are extensions that people are proposing for that, or on the IBGP side, then it will have some scalability implications. And the thing is that when you have instability, a lot of this stuff is multiplied by, when you look at it from a systemic perspective, it's multiplied by a factor of n, whatever that is, right? However many different, available paths you have. And so, one of the biggest things I didn't talk about, and I touch on it in the slides that are posted online, is like path hunting and path exploration and some of the challenges with that stuff, where you get different race conditions or other things. And so, there are a lot of dynamics when you look at it from a systemic perspective that are pretty challenging. And so, you got to think about it, because if you're just saying I'm going to configure this in this router and do this widget in this router versus taking a system level perspective, then you may be causing problems somewhere else that you wouldn't otherwise be aware of. So it is something, the ECMP and IBGP multipath stuff, for example, are places where it certainly is directly adjacent to this, and something that you should consider if you're looking at scalability or convergence or availability of that infrastructure. So that's pretty much all I have to say on that at the moment. So. Thanks. Hey, Sandy, question? Of course.
Well, you'll probably guess what I'm going to talk about. Sandy Murphy at Sparta. Could you go to the slide that said origin authentication is of little benefit?
No, I can't. Next question. No.
Oh, golly gee, can I ask you another question?
That's okay. No problem.
For those who don't know, I'm the CIDR working group co-chair at the ITF. And I would like to point out that Origin AS is recognized as not being a total solution to routing security, but it is also an absolutely necessary and essential step. Nothing else you do matters if you haven't fixed Origin validation.
Yes.
So I don't quite know how to phrase something that you know is an absolutely necessary, vital, and important. We must do this step, and still say very little benefit.
So I have a different presentation where I talk about just that.
Okay.
I completely agree with you I completely agree with you, as you well know, and I didn't attempt to trivialize it here. And the point is that there's a lot of work. So it's amazing for us all to sit in this room and the internet to be where it is today, and there to be no formally verifiable authoritative source for who owns what IP address. Yeah. And if you don't have that, and you can't say who owns what IP address and what origin is authorized to originate that IP address, then you can't secure the routing system. Right. And I completely agree with that. But you also the routing system itself is not going to be secure until you can associate who can advertise those origins. Because if you can spoof an origin or you can leak a route and hijack a route, then don't say it's secure if it's only providing 10% of a fix, right? So I completely agree. You have to have this for the foundation. I'm just saying that it's not the end all. So.
I know that you and I are in agreement about this. I just wanted to make sure that
absolutely.
The audience heard that this is a necessary. Absolutely. We must have to do this step.
I completely agree.
Anything else that we do.
Yep.
Okay. Thank you.
So
you're welcome.
Patrick next, then Randy.
Hi, Patrick Gilmore, Akamai. So the idea that a non-transitive attribute coming into a RIB causes a re-announcement to external neighbors is what I would call a huge throbbing bug and has been around for a couple of decades. Why is it not fixed? And where are the vendors in this room that are not listening to us as we have been complaining about this for decades? I mean, this isn't like a 6-month-old bug, right?
Yep. It's 11 years that it's identified. And, Labovitz and those guys early on were, and we actually talked to Kior Patel at Cisco and some of the other guys, and we identified some of the versions of iOS associated with that, and that is an implementation thing. What happens is basically is you pick a new prefix inside your routing system based on a new next hop or a cluster list or something like that, and then you go through your decision process. Okay, I'm going to use this path instead, and you're not keeping state and saying instead of not advertising this, because when I strip off those attributes, it's exactly identical to the previous prefix. I'm not keeping state of that. So your vendors should be working on that, and I completely agree. And you should ask your vendors where they are on this. And I would note that some versions of iOS have addressed this, and I'm not sure about JunoOS because we didn't look at that expressly on the eBGP side. And so talk to your vendors about it.
Right. Then I would encourage everybody else to do the exact same thing.
Yeah, absolutely. Good point, Pat.
It's gigantic.
Yep. Randy?
Randy Bush, RGNet. Yes, I still work at IIJ, but IIJ employees are not allowed to travel to the United States because of H1N1. Just to further clarify and to further the rat hole on routing security, there are 4 steps. One is, as you said, to have verifiable attestation of who owns, as it were, a prefix. Second is routing origin verification, that the announcement started at an AS who owns that prefix. And note that this would cure 95% of the bugs we have in routing today, the YouTube accident, 7007, 128/9, etc. The third is path validation, as you say. In other words, were you authorized to hand it to Lucy? You handed it to me. And the fourth is locking the data plane to the control plane, that the actual packets, which were paid to deliver, followed the routing path.
Yep.
And if any of JREX's students are here, Sharon, et cetera, they're doing some interesting work in that area, as are some other people. Sorry to rant on.
Oh, no, I completely agree. I don't think that Sandy or I disagreed with that either. So, good. Any other questions? Well, thank you very much.
Thanks, Dan.